warning after. Oh, okay. Should I activate my audio, or? Okay. So they tell me that you didn't hear me. So I will repeat that we have, okay, now everybody is back in. There is a beautiful day in Corfu, so people were reluctant, comprehensively, to come back. And the next speaker is Raimar Wulkenhaar from scalar fields on noncommutative geometries to blobbed topological recursion. And as usual, Raimar, I will give you a warning after 20 minutes. Then there will be 5 minutes to complete the talk, and then 5 minutes questions. Please.
Can you hear me? So I have no feedback. Does it work? So, okay, can you hear me? So, okay, I hope it works. So otherwise, please interrupt me. Anyway, good. So many thanks for the invitation. Unfortunately, I can't be with you. I really regret it, but there are many other things right now. All right, so let's start. This is about a project which started a long time ago. Especially the senior people will probably remember how it all started. Anyway, for me, a certain phase transition happened around 2009 when, together with Harl Grosse, we somehow understood that in these class of models, something special happens. All right, we were not able to locate it, but we knew that there is something. And in the meantime, so it means in the last 2 years, more or less, we understood what this structure is. And it's topological recursion, something I'm very happy with, because this is also relevant for many other areas of mathematics and physics. It's beautiful bridges between them, and so therefore I like it. All right. So in this distinguished audience, I don't have to introduce, explain what the lambda 5^4 model on non-commutative spaces. So you know it's problem of optimization, utilization, and so on. And in the end, it boils down to study large n limits in matrix models. Good. So okay, of course there are many matrix models, and what I'm interested in is a case of, say, non-commutative random variables, so matrices, and the covariance of the free field.
Raimar, can you talk closer to the microphone, because we have,
okay,
if we raise the volume, then we have some background noise, which is annoying. So if you can
is it better?
Raise your voice and speak closer will be appreciated here.
Okay, that was my feeling, that I have to do something. Right. So is this better now? Okay, so I tried to continue, but please interrupt me if it's not working. Good, so okay, the main thing is about covariance of the free field. So it's parameterized by spectral values of the Laplacian of your model. These EK, these are eigenvalues of Laplacian. And so that's important. Here's the difference to the traditional matrix model where you just have a constant here downstairs. All right, so this defines the measure, and then you deform it in the 5^4 way. Good, so then you build or study Dyson-Schwinger equations, which give a way to non-perturbatively define the quantum field theory. And here we are in the happy situation, and this is where the improvement compared with traditional quantum field theories happen, that these Dyson-Schwinger equations decouple in the large n limit on the 1/n expansion. So this first equation is here, is the equation which I derived with Harl Grosse a long time ago. And this equation contains everything. So all difficulties in this quantity theory, it's about realization, it's about the nonlinearity of the interaction. In particular, here is the quadratic piece, which makes the equation difficult but also interesting. Good. So again, everything is the free part of theory is built in a measure, in a spectral measure, and this essentially is the spectral measure of the Laplacian on the language geometry. Okay, so again, nice equation, but complicated, and unfortunately it took us 10 years to solve it. But okay, we have it. I will show you the solution. And then there are next steps. So the next step is about the other correlation functions in the 1/L expansion. It's clear they satisfy affine equations, so all solvable, but there's absolutely no guarantee that we can understand the solution. So again, nature is nice to us. We understand the solution, and the understanding is in terms of blobbed topological recursion. Good. So this will come. This is the plan of the talk. So here I describe how to solve this equation. The first step was with Eric Panzer, and then what I described here is with Harald Grosse and Alex Hock. Okay, so start with an ansatz. So that's the two-point function you want to know. You express it in terms of some unknown function tau in two variables. Good. So this function tau you declare is the imaginary part of the logarithm of a trivial y, that's the y here, and some other unknown function I. And this I is related to a further unknown function r as minus r of a negative inverse of r up to shift by the mass. So still nothing happened, just an ansatz. Everything is reduced to function r. So what is r? So R introduces another function, namely a measure function rho lambda, and essentially R is the integral transform of this measure, and then there's a trivial part Z. Okay, again, everything's shifted to a last unknown function rho lambda, and now we close the system, so we require that rho naught, that was the input, the given spectral function, rho naught of R is this function rho lambda inside. Good. Okay, so the miracle is that's the solution of the equation we had. So this equation is identically solved by this description. So we have to solve the system 3 and 4. I will show the equation in three most important examples, and then everything else is automatic. And the nice thing about it is it really uses mathematics which was available 200 or 250 years ago. Nothing new. Okay, but it took us a long time to understand. Okay, so three important cases. First case is rho is identical to 1. That's two-dimensional Moyal space. Then rho lambda is 1, so this is an integral, that's a logarithm. And then you have to evaluate R inverse. So you have to invert the function z minus lambda log of 1 plus z. That's the Lambert function. And so you have the solution. You have I, you have tau, and then you have g. Okay, that's easy. So more interesting is Moyal in 4 dimensions. So here the spectral function in the limit is rho naught of t is t. So the integral to solve is here. And now there is a potential danger. Namely, if also rho lambda grows linearly, then you need here downstairs of this t plus x factor epsilon to make this integral convergent. And therefore, here the second term grows as x to the power 1 plus epsilon, and it exceeds the first term. So therefore, this you think, and this is also what comes out from perturbation theory, that this model is only consistent up to cutoff, which is nothing else but the famous triviality problem of the lambda phi to the 4 model. But again, nature is nice to us. This equation has a beautiful exact solution given by the Gauss hypergeometric function. And the coupling constant is contained under the arc sign as a parameter of the hypergeometric function. So that's exact solution of the entire planar two-point sector of the theory. So, and the nice thing, well, it exists globally, in particular the inverse exists globally, and it shows from the behavior of the hypergeometric function that the interaction, the 5-to-the-4 interaction, effectively reduces the spectral dimension, which previously was 4, to 4 minus 2 times arcsine lambda pi over pi. So, and this dimension drop due to the interaction solves the triviality problem of the lambda 5-to-the-4 model. So from a physical point of view, this may be the most interesting result. And then we get exact form, integral formula for the two-point function. So here's a third important example, namely just finite matrices. That's our R depends on here on deformed spectrum, rho and epsilon, and the relation is to the initial parameters. So these E's, they were the spectrum of the given Laplacian, multiplicity at RK, and you have to solve this system of algebraic equations. Abstractly, this is always possible, so it gives us R. And then with R, we build the solution. So here, that's the function g of zeta, eta, which we want to know. Well, zeta and eta via R, you go to the pre-image, which is z and w. And the z and w you insert into a complicated but explicit formula, a rational function of z and w. And this gives then the exact value of the two-point function. So, and this observation here, this formula is the starting point for all the developments which I want to present now, which relate to topological recursion. Okay, it looks a little bit complicated, but in fact, it's an absolutely beautiful formula. Good, so now in second part, I come to topological recursion. So that there is a link was well suggested by the method. So matrix models are typical class of examples. Also that we use techniques of complex analysis that suggest that there's something. So I cannot in this short presentation explain what topological recursion is. Roughly speaking, it's about so-called spectral curves. Spectral curves consist of certain data, and one ingredient is, well, there are Riemann surfaces, or complex curves. And then there is a notion of ramified coverings. So map from one to the other with similarities. And then, moreover, you have meromorph differentials. Many of them, you give yourselves the initial one omega 0,1 y dx, and another one omega 0,2, well, that's a bidifferential. And this is more or less, in most examples, a standard form. It's a so-called Bergman kernel. Good, and from these initial data, there is a pictorial way how to build the higher omega gn. So G is the genus and n the number of marked points of the Riemann surface. So here's this picture. So the key ingredient is here this pair of pens, which is the recursion kernel K. It's over here. And this kernel is used to glue Riemann surfaces of smaller topology, so of larger Euler characteristic. Inside this pair of pens in all possible ways. And this gives then here the omega gn of the next complicated topology. So this can be made very precise. I will have in the formula in our case, and more or less that's also the general case. But okay, let's keep it this way. Good, so here are examples, few examples, few of very, very many. So there is, historically, there was the so-called Hermitian one matrix model, very important examples. It's exact description of two-dimensional quantum gravity, and the spectral curve is here. It's about ramification of the Riemann sphere. Here's this map X. Y is related to the potential. I will not explain. B is a Bergman kernel. Okay, and so integrability and all the things can be understood from this curve. So another important example is the Kontsevich model. So in some sense, this is the prototype example. It's the easiest example of a spectral curve. Namely, it's just given x of z is z squared, simplest function you can think of, which has some ramification, and y of z is z. So very simple. And then as conjectured by Witten and as then proved by Kontsevich, by this model, this model or the spectral curve and topological recursion computes intersection numbers on the moduli space of stable complex curves. So a deep result. And on the other hand, this can also be related to the matrix model of Kontsevich. So this is this typical cubic deformation of the same free theory as we had. And then you consider cumulants of this Kontsevich measure, and they essentially define the omega GNs. So these are the same as those computed from topological recursion. So there are also very sophisticated examples. So here's one from string theory. There are dualities. There's an A model and the B model. And so essentially the spectral curve of the B model, you take the omega GN of that spectral curves, and they generate the Gromov-Witten invariance of the A model. So, but there are many, many more examples. Good, and more or less we are in this situation, and that's what I want to explain a little bit. Okay, this is work of the last 2 years together with Johannes Banal and Alex Hock. So Johannes is a PhD student, Alex was a postdoc, and he continues now in Oxford. Good, so okay, let's start. So I told you what the two-point function is. This two-point function actually comes in two flavors. So there is one, so the basic example, this lives topologically on a disk, and the disk has a boundary, and the two matrix indices live on this single boundary of the disk. But there's another possibility, namely that's a cylinder. So which has two boundaries, and here the matrix indices, so one of the matrices lives on one of the boundaries. So every boundary has one index. Good, so this gives a total two-point function partially summed. Okay, take it as a definition, and this defines omega with one index. So, so these two-point functions, they depend on the spectral values Ek. So we can differentiate it many times, and then study large n expanding, and this gives rise to higher omega indices. Good. All right, so these things have a complexification. It's the same way as we came here from the matrix model to the, Dirichlet equation in continuous variables. So very similar. Good, so okay, so the problem is we have the two-point function only in the planar case, but not in general. So to get them, we pass through the omegas. And then there are two other families of functions, which I will not describe in detail. And they also have complexification, and all together form a certain system of equations which have to be solved in well, decreasing Euler characteristic. So here the box we know, that's two-point function. And then from that, you have a chain of equations to solve. Dirichlet equations, and well, inside the box, the solution is relatively easy, but going from one box to the other is difficult. But it is doable in principle, and I show you the solution. So if we have all the contents of these boxes, then we can compute any correlation function which we are interested in particular also the full two-point function, not only the planar case, but for any genes. So this step again are very easy. Complicated thing is to go from one box to the other. Okay, so then, well, we managed to do this in simple examples, and it's convenient to express everything in terms of, well, this omega gm. Namely, we have our omegas defined before, and then you multiply by differential subset of R of the variable. Good. And doing this, we find something astonishing, namely the first example, omega 02. So let's go here, that's this box, is described by, or solved by an extremely simple expression, namely the term blue, this is exactly the Bergman kernel. And then there's a contribution where one of the arguments is reflected. So very simple formula. And well, achieving this result is complicated, but the results themselves are extremely simple. Here is the next step, omega 03. Here, this is a dependence on parameters beta, and beta are the so-called ramification points of this ramified covering, defined as the points where the differential vanishes, critical points. So they give the poles, and there are other poles, well, here at x plus u equals 0. Good, so, and now the key observation is the blue terms are exactly those which are generated by topological recursion. So this graphical picture, in particular with the recursion kernel, I'll show you again one of the next slides, gives exactly, so this input, omega 02, but omega 03 is computed. Yeah, okay. Good. So, but there's more. There are the red terms, and they happen to be in in agreement with an extension of topological recursion. This extension is called blobbed topological recursion, was found or developed by Gaëtan Bourreau and Sergei Shadrin 5 or 6 years ago. Good, and we fit exactly in this framework, in this extended framework of topological recursion. So now I have two more technical slides. Well, to prove this, we notice that there is something special with the reflection. Z goes to minus Z. So in general formulation, that's an involution. So, and we consider spectral curves where the y function is minus x of a reflection of Z. Good. Then we take an omega which is purely odd under the reflection, omega 02 is purely odd, whereas the higher omegas, they have an even part. And the even part is expressed by a residue formula of something of lower topology. So let's accept this. That's an ansatz. So the miracle is, after hard work, this system can be solved, and the solution is here. So, okay, all omega 0 and arbitrary number of points can be recursively computed by such a kernel representation. So in particular here, this blue line in second line is exactly this picture of topological recursion. This K is a pair of pens, and it glues together two smaller Riemann circles. Small topology. And there is something else. That's the term in red. Again, represented by absolutely similar kernel, also this bilinear form in the omegas. So this term is new. And well, that's a description of the blob. And we have an explicit formula for it. Good, okay, that's the solution of the involution equation, of this equation. So very general. And now if we plug in our situation, that the reflection sends just Z to minus Z. The ramified covering X is our R, which we had from the solution of the two-point function. Then, so this formula with these special choices exactly give the solution of this, well, the upper box row of boxes. So it's a horrible system of equations can be solved in such a systematic way, and that's linked to blobbed topological recursion. So what's really special is there are many examples of such structures, but recursion formula involving a recursion kernel for the blob is relatively new. And we hope to understand it more, in particular higher genus, in the next time. We have some ideas, but that's okay for one of the next meetings. Good summary. So, okay, it started with Quantitative geometries, where many participants contributed and worked. And we understood that the special situation makes contact with a beautiful field of mathematics, namely topological recursion or block topological recursion. And so it means in particular that there are relations to other areas of mathematics, for instance, intersection numbers on the moduli space of curves. That's almost a triviality. But so we hope that because here our evolution is something natural, that it's nevertheless interesting. Also something to work out in the next future. A question which always comes is about integrability. This is not known in the blobbed topological recursion. However, we are a little bit optimistic because this involution is very special, and also the representation by a recursion kernel for this additional piece, the blob, is extremely special in this whole class. Therefore, somehow we still believe that there might be a chance to prove integrability of this non-commutative lambda phi to the 4 model. Okay, so that's what I wanted to communicate, and okay, let's stop here.
So, hi, Raimar, this is Harold. So first, very impressive work. Now, I actually have 2 questions. So the first is a simple physics thing, namely, so at some point you mentioned that this solves the triviality problem in 4 dimensions. Now, in what sense? Because I thought this is the self-dual model, right? So is there any phase or regime in that model where it describes propagating scalar fields in a flat space?
So I'm not sure that I got the last point, but of course, it's not the ordinary phi to the 4 model. That's the non-commutative. Where are we here? Good. So in particular, so there are 2 expansions. So one is in couple constants, which we solve completely. But there's also this 1/n expansion. And to really establish, so the planar, the statement is true for the planar case. But whether or not the whole 2-point function summed over all the topologies is non-trivial is something which remains for the future. So there are works by Bertrand Hénard about the large genus behavior of these objects, and there are still some things to do. But as soon as this, that's a highly active problem in research there, as soon as this is solved, I'm confident that we will somehow manage to say something about approaching the ordinary lambda phi to the 4 model from the noncommutative side. It's a boundary case, and it could be that in this way one can establish non-triviality also of the standard commutative lambda phi to the 4 model. Does it answer your question?
Yes, thanks. And then there is a short, more. I'm just curious. So as far as I recall, for the genus 0 part, you were able to obtain all endpoint functions from in terms of the 2-point function. Do you expect that this also works for the higher genus stuff?
Sure. Yeah, this part is easy. So the difficulty is to understand all these omegas. So here for this model, they are somehow auxiliary functions, but they contain the mathematics. And so this will come. So in 1 or 2 years we will have it. So this part is easy.
Okay, thank you.
Okay. I don't see other questions. Let me see the chat. There doesn't appear to be more questions. So we thank again the speaker, Raimar.
Okay. It was a pleasure.
And the next speaker is, I forgot.
So I have to unshare, right? Yeah.
It's Volker Schomerus, sorry. I knew who they were, the speakers, but not the order. And I'm glad to say that it appears that the speakers are all present with us. So the next speaker is Volker Schomerus, and cyclic cycles in, sorry, I'm reading the wrong line, from scalar fields on non-commutative geometries to, sorry, I am making mistakes in reading my.
You're doing really, it's okay.
Schomerus, Supergroup, Chern-Simons theory, and topological spaces. Okay,
Right.
sorry.
Thanks a lot. I'm really quite impressed how smoothly this runs, this hybrid
Look,
from really
that
challenging.
was a mistake. Long lines, and so I was mixing things. Please.
No problem. Thanks a lot for this stage. I would very much have loved to come to Corfu this year. Unfortunately, it wasn't possible. I envy all of you who are there now. So yeah, I changed my subject, looking a little bit at the theme, in particular this morning, and brought it closer to non-commutative geometry. So I'll report today at some recent and ongoing work in collaboration with Neshla Agay, Asad Gainudinov, and Mikhail Pavelkiewicz, which is devoted to supergroup Chern-Simons theory and topological phases of matter. Now, this may, for the audience here, not sound like very close to home. I promise I won't talk about topological phases of matter very much. I will soon go straight to a quantum group non-commutative geometry, much closer to the home, but maybe I felt it was still worth to tell you for a few minutes, or on this slide at least, sort of the physics context in which I think this is embedded. So bear with me, and if you're, as I said, in 2 slides from now, you will be firmly in non-commutative geometry. So it's an important topic, in fact, in physics right now to classify new states of matter, these topological phases of matter. It's interesting to classify them because it's a completely new types of systems for which there doesn't exist sort of, or it's just emerging classification scheme. They also are believed to have important applications, in particular in fail-safe quantum computing. And so two things that you would like to have in these systems is, first of all, what you observe to have often is a non-trivial ground state degeneracy. So you have a protected space of ground states with a non-trivial degeneracy. When you put these systems, let's say maybe on the surface of a genus G, so you have, of course, in these systems excitations which have sort of anionic statistics, and you need sort of a rich, in particular, that means non-abelian grading properties of these anionic excitations in order to be able to construct enough interesting gates in your quantum computer. So the first example in this context that was constructed was his famous Kitaev's toric code that has the first property. It has a non-trivial ground state degeneracy, but somehow the braiding properties are not rich enough. And then this was generalized. There's Kitaev models and equivalently Levin-Venn models. This was all development in the early part of the century, which provide a rich framework of construction for such systems to compute sort of ground state degeneracy and the braiding properties of these anionic excitations. Now, one thing that is also visible from the construction is that in some sense, these models one can think of as a square of the Hamiltonian Chern-Simons theory. And that is now a move a little closer to the subject of my talk. In fact, about 4 years or 5 years ago, Katrin Moisberger, who is also here at this conference and will speak later, she actually showed that Kitaev and Levin construction of these ground state degeneracies and sort of braiding properties is actually something that fit in a scheme that was developed about 10 years earlier, sort of in the mid-90s. In fact, by Alexeyev and also Harald Grosser, the same Harald Grosser that appeared in the previous talk, and myself, in order to quantize Chern-Simons theory, we designed some kind of setup of a lattice gauge theory where the lattice fields now don't take values in a group, but in a quantum group. And we showed that in this way we could quantize Chern-Simons theory. And when in this scheme you put in a special kind of non-commutative gauge symmetry, being a Drinfeld double of some Hopf algebra, then in fact you recover Kitaev and Levin models. And that was shown by Katrin Moisberger, who herself has contributed a lot to developing this quantization, so-called combinatorial quantization of Hamiltonian Chern-Simons theory over the last years. So the goal of my talk today is to show that, that this combinatorial quantization provides a very beautiful or framework to actually extend the constructions to allow for superalgebras or graded symmetries. So if you think in the world of Chern-Simons theory, this would mean Chern-Simons theory with the group being not a group, but a supergroup. And of course, in the world of topological phases of matter, that would mean that we're now kind of turning towards systems where, I mean, topological phases in matter systems which contain bosons and fermions, not just bosons as in the ordinary case. So now let me talk about the plan. So again, I mean, the idea is to construct these theories associated now with Hopf superalgebras rather than Hopf algebras in this framework of combinatorial quantization, and to show you how to compute ground state degeneracies and the braiding properties of the anionic excitations of these within this framework. And all this is it's enormously algorithmic and relatively easy to do. Now, the framework of combinatorial quantization, I alluded to this already. We developed this in the mid-90s together with Harald Grosser and Anton Alexeyev. It was then developed further. In fact, Katrin Moisberger and Bert Schwarz, and also Bufino Rush in particular, developed, extended it to non-compact groups. This is maybe not quite the focus of today. There was also some extension to non-unitary theories, which is a little closer to today's field, although I won't dwell on that too much. And in fact, the whole framework was also picked up in mathematics in the context of factorization homology, and mathematicians actually contributed towards reformulating a little bit the old approach that we developed. And so the plan for today is that mostly, of course, don't have that much time. In fact, I've already used the first 10 minutes. I will review the combinatorial quantization of Chern-Simons theory, but I'll do that in a modern language that incorporates some of the things that have been done before. And in this modern language, actually, the extension to supergroups is essentially straightforward, at least in the formulation. Of course, then the computation, there are some subtleties, new subtleties. I mean, of course, those of you who have worked with supergroups and superalgebras before may know that it's going from a group to supergroup is not that trivial. It's not just putting in some grading and then you're done, but there's really completely new features that happen. And if I have time, I will show you some of these. And that also explains why sort of in other approaches, including these sort of fermionic matter, has been a bit challenging. But all right, so I don't know whether it's appropriate to ask for questions. This is the end of the introduction. I now goes to the more technical part. So again, we'll see how detailed I can have this description, but I hope I will at least be able to give you sort of a flavor of how this goes. So the construction that we designed in the 90s is based on a central input, which is basically the gauge symmetry. So you want to build some kind of quantum group valued lattice gauge theory with a gauge symmetry, which is described by a Hopf algebra, in our case now a super Hopf algebra, with certain extra properties. It has to have an R matrix, so that you have a notion of braiding. There's some technical assumptions on factorizability, and it has to have a ribbon element, and also a right integral, which is a map from the Hopf algebra to the C numbers. Now, all these objects, of course, satisfy a long list of axioms, which I think people working in this field have all seen before. And if I would flash them, it wouldn't really help much. So, so we'll assume that all these properties are satisfied, and that's what's meant by this quasi-triangular factorizable ribbon super Hopf algebra. And now, so that's the gauge symmetry. Now we have to find the gauge field, and in lattice gauge theory, of course, the gauge fields are associated to the links of the lattice, and so they're usually taking values in the group. That's the holonomy of the connection along the link. Now, in this non-commutative gauge theory, we replace this holonomy or the algebra of functions on the group, let's say, by a non-commutative algebra, more or less a very close relative of a quantum group. So the dual of G, but it's not quite that. I will just symbolically write this here through this equation, which is these famous RTT-like equations that define sort of quadratic relations which define the algebra of functions on the quantum group. Now, these relations have a nice property, namely they preserve a lot of gauge symmetry. If you have this algebra, you have actually left and right action of the gauge symmetry corresponding to gauge transformations in the initial point and final point of this link. So this is sort of the basic setup. And now what is quite beautiful is that so you start taking a bunch of these quantum group valued gauge fields. And now we put them together in a way that encodes sort of the geometry of a surface. Okay, so that's the basic idea. So you choose some kind of graph or lattice that you can draw on a surface, let's say a torus or plane, or maybe even a surface of higher genus. I'll come back to that in a moment. And so you have a bunch of links, and you now want to put them together. So each of these links, individual links, you have associated one of these quantum group-like algebras, but now you want them to put them together in a way that preserves gauge symmetry. And there's of course, you cannot just put them together as commuting copies in order to preserve gauge symmetry. Whenever two links meet at a common vertex, in order to get gauge symmetry at this vertex, you have to actually have braided commutation of these things. So that's the first relation here. Of course, if they links have nothing in common, no endpoints in common, you can just let them commute. And you can also reverse your orientation of a link. So again, this definition here takes a bunch of quantum group-like algebras, puts them together in a very large new non-commutative algebra that kind of feels the topology of a surface. And it does that in a way that preserves gauge symmetry, where now gauge symmetry acts on all the individual vertices of this lattice. And so it's just designed to do that. And now you can construct an algebra of observables like you would do in lattice gauge theory. It's an algebra of gauge invariant objects. So you have this larger non-commutative algebra of quantum group holonomies. And within there, you find the observables, which are gauge invariant objects. And this algebra of observables in particular has lots of interesting properties. It turns out that it depends actually not on fine details of the graph itself. It just turns out to depend only on the number of faces of your lattice. So for each plaquette, for the number of plaquettes, and it determines sort of the type of the algebra, and of course on the gauge symmetry. So so that's the basic setup. And again, sort of the beauty, and also why mathematicians got interested in this, is that it in a beautiful way computes, combines the non-commutative algebra with geometry, and that's sort of where all the gist of the matter lives. Now, since it's the algebra of observable is largely independent of the choice of the lattice, it turns out that you can choose like a very special lattice. I mean, the most special lattice is one fact that's only a single vertex and as many loops as you have roughly, I mean, loops corresponding to the plaquettes. So I will do this here. So so this is now a special construction of the algebra of observables, where I associate. So first of all, I take this this Riemann surface of genus G, and I put that. In fact, I take one that has a single boundary component. That's somewhat important. And then a number of punctures I admit, 1 to n-1, the punctures is where we will have the anyons, so that's a thing. And then I'm going to write down a lattice which has 2 cycles for each handle, or 2 links, closed links now for each handle, and 1 for each puncture. So there's a total number of 2g plus n-1 of these loop holonomies. Now the loop holonomies are not quite like the link holonomies I described on the previous slide, but you can make a loop out of 3 links. So if you use the rules that I gave you on the previous slide for how to make links, open links, sort of non-commutative, you can actually see that the monodromy along a closed loop satisfies also some kind of quadratic relations, which are these type of quadratic relations. And the experts in the field know that, of course, this quadratic algebra, in fact, defines something that is isomorphic to the original Hopf algebra that we started with. And then when you have handles, you see there's 2, each handle has 2 loops attached, and they're kind of put together in a funny way because one starts first and the second, then one comes back, then the other. So that defines an interesting algebra, which is called the handle algebra. It has 2 loop subalgebras, but they're intertwined through this funny relation. Sorry. And now, so this again is a description of this algebra, and so this is the graph algebra, and from this, of course, you have the algebra of observables, for which you want to construct the representations because you want to understand the ground states of your topological phase. That's the representation space of this algebra of observables. And there's an important theorem that we proved already back in the 90s, around 95. You see, I mean, this algebra here that we just constructed, that is associated to the surface of genus G with n-1 punctures, is a complicated non-commutative algebra because all these copies of the loop algebra, of these quantum monodromies, they are braided commuting. And so it may not be entirely obvious how to represent that, but it turns out that when you tensor that with the gauge symmetry, you can actually do some sort of decoupling and find an isomorphism of this algebra with an ordinary tensor product of G copies of this handle algebra and n-1 copies of the Hopf algebra. And this part here, you know more or less how to represent. I mean, this tensor product of G to the n-1 is just choosing n-1 representations of the Hopf algebra that you start with. And the handle algebra turns out to have just a unique representation. So the handle algebra is actually a Heisenberg double. So it's very much like Heisenberg algebra. So it has just one unique representation on the representation space, which is isomorphic again to G. And so in this way, you can actually easily build representations of this graph algebra. So you can represent this graph algebra through matrices if you want, on a space which is composed as a tensor product of representation space of this handle algebra and representation spaces of the Hopf algebra. And sort of the choice of representation here corresponds to basically the choice of anyons that you put there. So this choice here is basically the anion charges. And so you have this choice of representations. And of course, you're not really interested, I mean, in representing this complicated non-commutative algebra itself. You want to really construct representations of the algebra of observables, but the algebra of observables are gauge invariant objects. And so this complicated non-commutative algebra, of course, contains the subalgebra, gauge transformation tensor, these gauge invariant objects. And so now we can take this representation space and decompose that with respect to the action of the Hopf algebra, the gauge symmetries. So the representation I denote carrier space I denote by HP pi n, and then obtain these multiplicity spaces. It turns out that typically any given representation of the gauge symmetries comes with some multiplicity, and these multiplicity spaces, these are the spaces of ground state. So you want them to have non-trivial multiplicity, and they come now equipped with a representation of the mapping class group. And it's actually possible, of course, to compute, construct these spaces. It's more or less by just what I just described here, compute their dimensions. And these are the spaces of ground states in your topological phase of matter. Now, this comes equipped with a lot of structure. Since I'm kind of getting close to my time limit, I'll be very quick on that, which is a representation of the mapping class group. It's a generalization of the braiding properties. And in fact, in topological phase of matter, people know that even genus 2 properties are important to actually distinguish different topological phases. So they also really study a mapping class group on higher genus surfaces in order to distinguish topological phases. And so mapping class group is generated by something that is called a Dehn twist. So you take your surface, you cut it along a circle, and then you glue it, you turn one side by 2 pi and then glue it back in. That's what is a Dehn twist. And for each of these Dehn twists, you can actually associate an observable in your Chern-Simons theory, or in this algebra of observables, and so that you can construct explicitly. And there's a system. This is maybe somehow the main result of this talk, although of course in a very condensed form. There exists a very beautiful universal formula that does that for you within this framework. So the idea is that, of course, each circle on the surface can be written in terms of as a combination of the A and B cycles and these circles around the punctures. So for each curve on the simple curve on your surface, along which you want to make a Dehn twist, you have actually a unique lattice monodromy attached. And then what you do with this lattice monodromy, you can actually attach to that a unique observable through this formula, which involves this right integral and the ribbon element. And so in this way, you get observables. Yes, I am aware. Thank you. You get this set of observables, and this gives essentially a construction of these of the gates in your topological phase of matter. Now, this formula, in fact, of course, I won't be able to unfold to you completely. It's now a version, formulation of a formula that we had already back in '95, but in that case, for compact unitary case, only this formula, the way it's written here, is equivalent in that case, but for super algebras, it's an appropriate extension that takes into account the difficulties in dealing with super algebras. Now, since I'm running more or less out of time, I will go very quickly through the second part. So what I've described here is basically this basic framework, and I showed you the basic ideas on these 2 slides of how to construct the ground state of these topological phases, if you want, and also the braiding properties of these topological phases through very simple universal formulas. Now, of course, this all looks very abstract, and I had planned to show this to you in the simplest example, and so I will flash that now. So the simplest example that you can think of, in fact, of this that goes beyond. So when you do this, of course, for ordinary abelian gauge group, you don't get non-trivial degeneracy of ground state. So you have to do something beyond abelian gauge groups. And so, but the simplest thing you can actually do is to add some fermions and have a gauge symmetry which has sort of fermionic gauge transformations. And so, so the Hopf algebra that we plugged into this construction now is given by this relation. There's 2 commuting bosonic generators and 2 fermionic generators with these nice set of relations. And in this case, you can check that it has all the properties. You have an R matrix, ribbon element, and also this right integral. So let me not go through this. And then you can classify representation of this algebra. And it turns out that, of course, the typical representation of this is 2-dimensional because you have fermionic creation and annihilation operators. And And so you can find that there's roughly a p² different representation. That means p² different types of anyons, where p is any odd, can be any odd integer. And so here I give you representation matrices. And so typical representation, as I said, are two-dimensional, but when this E quantum number becomes 0, then it turns out that these representations become a little bit unusual, because you can only go with the fermionic creation operator from the bottom, from one state to the other, but not with the annihilation operator back. So in that case, you get one-dimensional typical representation, so-called atypical representation. That would correspond to very simple anionic objects, which are more or less like in the Billion gauge theory. And then you can also have, but I won't have time to talk about this, but this is really the specialties of super algebras. You can also have four-dimensional indecomposables, and also they play an important role in the story. And so now you can go through the rules that I've taught you before, and you can start to compute these ground state degeneracies. So you do that by computing tensor product of representations of this algebra that I gave you before. If you compute the second tensor product corresponding to the two-punctured disk, just inserting two anyons, you find that you get only two representations. And so whatever you do is you only get trivial ground state degeneracies. But as soon as you start adding another anion to the theory, you start to get non-trivial multiplicities. And so in this case, you can easily build interesting ground state degeneracies, which are non-trivial. And so the first example of this would be the case when you have basically four anions immersed in the theory of these relations between their charges. You can also study, of course, the systems on the surface of higher genus. I didn't really discuss enough the kind of details of that to really expand on that. But you see that on higher genus surfaces, you get a very large growing degeneracy of ground states. Then you can, of course, construct, as I told you before, these quantum gates. So there's a universal formula in this case for how to do that, these Dehn-Twist generators. And you can really compute this, of course, convert it into explicit matrix formulation. In particular for the torus, we have done that in the publication almost 3 years ago. But you can do this for any number, any genus and any number of punctures. And you get very interesting representations of this mapping class group that, again, are used to distinguish different topological phases. Now, this, I think, brings me to the end. Let me just conclude by saying that this combinatorial quantization of Chern-Simons theory that we developed in the 90s together with Alexeyev and Harald Grosse assigns the same state spaces and representation of mapping class group to a punctured Riemann surface as the construction of Kitaev and Levin-Wen, which were developed almost 10 years later. And this is, of course, something that was pointed out by Moisberger about 5 years ago. Now, what I've shown to you that this combinatorial quantization is a very beautiful framework that, in fact, you almost didn't notice that I extended it to graded super algebras here. Although when you start thinking about it, I mean, essentially formula for the Dehn-Twist that I showed you, that's very crucial. There's some crucial things happening, which I didn't really have time to talk. But I think it's a very beautiful framework that extends, of course, the framework of Kitaev and Levin-Wen, and applies naturally to systems of bosonic and fermionic topological order. And I've tried to, although this was a bit sketchy, show you the simplest example of that, of this kind of super algebra gauge symmetry, and try to convince you that there's already, in this case, very interesting representations and ground state degeneracy and representation of mapping class group. And with that, I want to finish. Thanks for your patience.
Thank you, Volker. And there are no questions. Okay.
I see Catherine raising a
hand. I have a question.
Yeah.
About the supergroups. I mean, can you associate supergroups systematically to like every Drinfeld double that you could formulate a Kitaev model or a Levin-Wen model for? So does any model admit for the inclusion of these fermionic states?
No, I mean, I think, sorry, so the Levin-Venn and Kitaev model, I don't think there's a systematic extension to super algebras, right?
Yeah, that's what I was wondering. Is there
My understanding is that this is sort of an issue with these models. That it's not so obvious how to do this extension. So I mean, the example that I showed you, I think, is an example of a double of a graded. I mean, this UQGL11 is an example of a double of a graded Hopf algebra.
Okay, so maybe I ask this in a confusing way. So suppose that you have some like some Drinfeld double of some Hopf algebra, where you can do combinatorial quantization, only that it's limited to a Drinfeld double now. Could you associate to this always a fermionic model with a supergroup?
I can always do that. Actually, I haven't. So I mean, so your question is, yeah, I can systematically, I mean, take let's say, for instance, a billion groups, or no, sorry, finite groups, and then make a super Hopf algebra, associate that to them, for instance. I actually don't know what the answer is to this. So to claim is, again, if I start with a Hopf algebra, which is with the graded Hopf algebra, then I can run this construction and compute the ground state degeneracies and mapping class group representations.
Okay, I guess it would require some classification results on supergroups that just doesn't exist at this stage. I mean,
yeah, that's probably true. I mean, if you wanted to do it in terms of this classification, I mean, you have, of course, tons of interesting examples, right, of such Drinfeld doubles with graded Drinfeld doubles, but yeah, I don't think it's a big classification.
Okay, and maybe one more question. Basically, you include fermions in the models, but the models also have anyons in the sense of that's representations of the braid group and can have any spin. How is the kind of fermion spin 1/2 interacting with the anyonic spin? Can you kind of give a simple physics picture, or is this quite complicated?
Well, yeah, I mean, okay, the fermions basically would be there sort of. I mean, the anyonic states. I mean, these representations, of course, that are associated to the anyons, they have sort of a fermionic and bosonic part, right? So all these states, yeah. So I mean, these two-dimensional representations have kind of one bosonic and one fermionic piece in it.
Okay, but if you had just a model with anyons, you could also have 1/2 in principle. Like if you didn't include.
No, but I mean, okay, so this is, yes, but I mean, okay, again, this is more general in the sense that if your initial material, I mean, had bosons and fermions, right, you would expect to get states with even and odd, I mean, bosonic and even and odd grade. And so this clearly gives a much more general class of ground state degeneracies and mapping class group representations.
Okay, so it's like an additional physical degree of freedom that is also.
Yeah, so you mentioned, I mean, most of the study, of course,
not.
of Levin-Venn addresses sort of bosonic systems, right? Because of course, also in experiments, they are most easily realized, I believe. That's why most of the work focuses on that. But I mean, in cold atom systems, I think it's much easier to build sort of topological phases based on bosons. But in principle, the fermionic excitations are relevant. I mean, you could also imagine, even if it's a little harder to realize experimentally. And so this is an extension relevant in that context, when you also have sort of fermionic degrees of freedom in the original fermionic matter in the original material, and you look at the topological phase in there. Yeah.
Okay. Thank you very much.
I think we should proceed towards the next speaker, but we can before that Volker again.
Thank you.
And the next speaker is Leonardo Castellani.
Hello to everybody. I will try to share the screen.
There, the title is Supergravity with integral forms, and let's check the audio, and you have to share the screen, I suppose.
Okay, do you hear me?
Yes, we can hear you.
Okay, I'll try to share the screen.
And you know the rules. After 20 minutes, I will tell you that there are 5 minutes left. And this, we can see the screen, and probably you can put it without the little miniatures on the left to make it full screen, but it's not really relevant. Okay, please.
I have to understand how to do it. Wait. Maybe presentazione. Is it, do you see everything? Hello? Do you hear me? I don't hear you.
And yeah, you have to be careful. Presentazione will change the slides. Just put full screen instead of presentazione.
Oh.
Okay, now it should be okay.
But you see it now?
We see your screen anyways.
Okay, so I think I will proceed in this fashion. Okay. So I thank the organizers for this nice opportunity to present some work that extends some presentations that I did 2 years ago, still in Corfu, for the first part of this talk. The second part of this talk will be about integration on supermanifolds applied to supergravity. The subtitle, well, doesn't work. Okay, so there is a problem. Sorry, I will just...
You interrupt, go down, there is an X, you can see in the bottom.
Yes.
Yeah, put this, yes. Okay, now instead of presentazione, you have to put full screen.
Full screen.
So when there is view, this.
View, tutto schermo.
Attività, modalità, tutto schermo, esatto.
Okay, that's it.
Okay, now you change with your arrows.
I changed the arrows. How? Well, I don't know. The subtitle of this talk should really be the usefulness of differential forms. And this is what I will apply in this talk to discuss two subjects that are in fact related. It is clear that differential forms are natural for constructing geometric actions in the sense that it yields immediately coordinate transformation invariant action. All Cartan calculus is absolute calculus, which does not refer to coordinates. And this treatment of geometric theories, for example, gravity or supergravity theories, suggests immediately Hamiltonian treatment that preserves these covariants or invariants under general coordinate transformation. And this is what I will speak in the first part of the talk, extending what I did 2 years ago to the fermionic case and the supergravity case. Then this formulation of supergravity actions in terms of forms and superforms brings us to the subject of integrating on supermanifolds and to discuss the analog of a top form in supergeometry. And the top forms in supergeometry are called integral forms. And this is how I wish to reformulate a program of geometric construction of supergravity actions that was developed in Torino. I want to reformulate it in the language of integration on supermanifolds and using integral forms. I will not have time to see some applications to non-commutative extensions of supergravity theories that again use differential forms in their formulation. So this is these are some of the papers I will base my talk on. Most of what I will say about integral forms has been developed in collaboration with Pietro Antonio Grassi, Catenacci, and Cremonini. And this is the index of the talk, which summarizes what I just said. Now, 2021 is the year where supergravity becomes 45. That is 45 years of supergravity after its discovery in 1976 independently by these two groups, Friedman, Van Nieuwenhuizen, Ferrara, and Deser and Zumino. Now, let's plunge immediately into the matter. The action of supergravity, the usual component action, is the first one that you see on this transparency, which has the Einstein-Hilbert term and the Rarita-Schwinger term. You can reformulate it in form language. This is a standard where the definitions of the Lorentz curvature and the gravitino field strength are given here. Now, this is quite standard, and you know the invariances of this action. Diffeomorphisms, obviously, these are obvious in the form formulation. Local Lorentz rotations and local supersymmetry. Local supersymmetry is less obvious. You have to work to prove it. And these are the transformations on the Vielbein and the Rarita-Schwinger field, the gravitino, that realize local supersymmetry, okay? This is standard stuff. Now enters Hamilton, and what the logic I want to apply is the following. The usual Hamiltonian formalism, prescribes to take derivatives of the Lagrangian with respect to the time derivative of the fields, right? Where the fields are considered zero-form fields. This is the standard traditional stuff. Now, I want to use form language and make use of the advantage of dealing with forms. Then momenta will be defined now that Lagrangians are given in terms of forms, as you see here. You see this Lagrangian, this geometric Lagrangian is given in terms of one-form fields, the Vielbein and the gravitino, and a two-form field, which is the curvature. So now Lagrangians are given in terms of forms, and then I define momenta as the derivative of the Lagrangian with respect to what? Well, the analog of a time derivative of the field now is the exterior derivative of the field, right? Since in the Lagrangian fields appear via themselves and exterior derivatives on the fields themselves, so I differentiate the Lagrangian with respect to the exterior derivative of the fields. How do you do this? Well, there is a prescription. There will be a left and a right derivative in the sense that you commute the delta phi in the Lagrangian to the left, and then you cancel it with this d phi. And this is how you take the derivative. This takes immediately and automatically care of the grading of exterior derivatives and the p-form fields. Now, these fields are in general not only one-form fields, but they can be p-form fields. And the Lagrangian will be a d-form Lagrangian if I want to have a theory in d dimensions, okay? This philosophy was introduced by Dada, Nelson, and Regge many years ago in the 80s. Now, here we wish to develop this philosophy. And the development is as follows. This is in general a Lagrangian integrated on a manifold, d-dimensional manifold, you can implement the variational principle, varying the fields inside the Lagrangian and imposing that the variation is 0. And this produces you Euler-Lagrange equations, which are d-1 form equations. Okay. And these are the Euler-Lagrange equations that you can write in form language. And these are totally equivalent to the Euler-Lagrange equations you would obtain via the traditional method. Now, you can implement a form Legendre transformation, exactly as you do in the zero form case. That is, you can define these momenta. These momenta, as you see, are d minus pi minus 1 forms, where pi are the forms of these fields, are the degrees of the form of these fields phi, right? Because d phi is a p plus 1 form, and you're subtracting from the d form Lagrangian, so it gives you a d minus p minus 1 form. The momenta are d minus p minus 1 form. You can construct a d-form Hamiltonian, the usual pq dot minus L Hamiltonian, where now the q dot is really this exterior derivative on the field. This, you can see if you sum the degrees of d phi and pi I, then you obtain d. And this is a Hamiltonian, and you can prove in the usual way that it depends only on the fields and on the momenta, and not on the velocities, which are now these exterior derivatives on the fields. You find the Hamilton equations, which are, you can prove that they are equivalent to the Euler-Lagrange equation, and they have the familiar form that the derivative of the fields are the partial derivative of the Hamiltonian with respect to momenta, and the dual form for the exterior derivative of the momenta. And okay, and this all works. You can also define a form Poisson bracket. You can take inspiration from the differential of a function of fields and momenta, which is written like this, and then you use the Hamilton equation and you find these. And then the Hamilton equations for any function of fields and momenta is just this form Poisson bracket so defined. The form Poisson bracket is really a form. If A and B are the degrees of the forms of capital A and capital B, then the form Poisson bracket is a form of degree A plus B minus D plus 1, since phi and pi are forms. If you multiply phi and pi, you find a d minus 1 form. So you have to subtract d minus 1 from A plus B. In particular, you find the conjugated Poisson brackets between fields and momenta. Okay. You can derive with a little of work the properties of the form Poisson bracket that generalize the properties of the usual Poisson bracket. You have anti-symmetry, where anti depends on the gradings of these forms, derivation and Jacobi. Here, there are two kinds of gradings, the grading of a form because it is a P form, and the grading bosonic or fermionic of the form, which is encoded into these etas. The eta A is 1 if capital A is a fermion, is 0 if capital A is a boson. And you have the usual Jacobi identities and so on. This sets up the formalism. Then you can, of course, use this formalism to start investigate the theory, the invariance of the theory under symmetries. You can define then infinitesimal canonical transformations that are generated by the form Poisson bracket. The generator of infinitesimal canonical transformation must be a d minus 1 form, because only if it is a d minus 1 form, the Poisson bracket of any function with the generator is again a d minus 1 form. So it is a variation a variation of a d-1 form must, of a p form must give a p form. And this happens only if this variation is generated by a d-1 form, as you can find simply computing the degree of this Poisson bracket, the form degree. You can show it, it is easy to prove in the usual way that mimics the classical way to preserve, that it preserves commutation relations done with the Poisson bracket, and that the commutator, in the sense of the Poisson bracket of two generators, yields again a canonical transformation that preserves the Poisson bracket. So the group structure is preserved. Action invariance can be investigated, and you find the analog of the Noether theorem when you consider global canonical transformations where generated by a function G, a generator G. What you find is that if you rewrite the action in Hamiltonian terms, this action will be invariant if and only if the generator commutes with the Hamiltonian, with the form Hamiltonian. That is, the d-1 form generator commutes with the d form Hamiltonian in the sense of form Poisson bracket. You can define Noether charges. You can see that they are conserved in the sense that if you foliate the manifold, then the coordinate parametrizing the slice foliation, the orthogonal coordinate with respect to the foliation, you can call it time, and this is your choice that you can do here, but we do not need, we never need to invoke a time or other sort of coordinates. This only if you wish to have a conservation theorem. But the interesting thing is when canonical transformations are generated by generate local transformations. This happens when the parameter of the infinitesimal parameter of the transformation is local, in the sense that it depends on space-time coordinates. Then, as we know, both gauge transformations and diffeomorphisms involve derivative of the parameter. Now, here, the only derivatives we have at our disposal are exterior derivatives, so we investigate the canonical transformation generated by a function, phase space function of momenta and of the fields that contain the parameter x-dependent and its exterior derivative. Okay, so if G is a P form, clearly F will be a P-1 form. Okay, and this whole thing must be a D-1 form. So here again, we investigate the variation of the action, and what we find is conditions on these pieces of the generator, these FPs and these GPs. These pieces must satisfy these two conditions, that is, the GPs must commute with the Hamiltonian, and the FPs must give a commutator with the Hamiltonian equal to G. These are all formulas that hold up to constraints if we are in a constrained Hamiltonian setting, which will be the case for gravity. This reproduces is at the basis of an algorithm to compute all the gauge generators of a theory in the Hamiltonian formalism, in particular in constrained Hamiltonian setting, that was first proposed many years ago in Annals of Physics, and this is its generalization to the form setting. Okay. Now, let's apply all of these in an example. We'll apply it to supergravity. Supergravity with auxiliary fields, so that supersymmetry is closed on shell. This model was constructed in the 80s, and the basic fields are the field bind, the spin connection, and two more fields, one form field A and two form field T. And you see the degrees of freedom add up to 12, and which match the 12 off-shell degrees of freedom of the gravitino. So you can write down the Lagrangian. It has these extra terms that contains the auxiliary fields. And these are the definitions of the curvature that you find in the Lagrangian. You can define here, I will sketch this very quickly because it's all, the logic is clear. These are the results. These are the momenta. All the momenta definitions are primary constraints since they do not involve velocities, that is exterior derivative of the fields. So I have these constraints phi that are primary constraints. I can construct the Hamiltonian with the usual construction PQ dot minus L. And this is the result for the Hamiltonian. From the Hamiltonian, using the form Poisson brackets, I have the equations of motion, that is the Hamilton equations, where I consider the Hamilton equations for the exterior derivative of the momenta. I have these things. These Hamilton equations, if I use the constraints, I find immediately the field equations of the theory. And these field equations that I wrote here coincide with the field equations that are well known for d=4 supergravity with auxiliary fields. Okay? These field equations fix the unfixed velocities that were these three velocities in terms of canonical variables, whereas the velocities, that is the exterior derivatives of the spin connection and the Rarita-Schwinger field, are constrained by these equations to satisfy Einstein and Rarita-Schwinger equations. Einstein equation is the first equation that you see here. The Rarita-Schwinger, yes?
You have 5 minutes.
Very good. Okay. You find the algebra of constraints, you can construct a Dirac bracket, and you can construct canonical gauge generators that via the form Poisson brackets generate all the symmetries that you know are symmetries of d=4 supergravity. Okay, this is a summary of what I just said. No time direction is selected. Everything is well adapted to geometric theories with p-forms. The constraint analysis a la Dirac is much simpler in this framework, and in fact you can compare it with the traditional analysis that was done many years ago for supergravity, and it is really an order of magnitude easier. And it is, of course, ready to be extended also to non-commutative settings. Now, of course, also Yang-Mills theories can be formulated in a coordinate-independent way, and in fact, we can go further and unify diffeomorphisms and gauge transformations by considering everything as every symmetry as originating from a diffeomorphism on a supergroup. This is an approach that has been developed in Torino since the 80s. What we consider is a form Lagrangian, D-form Lagrangian, integrated on a submanifold MD, D-dimensional submanifold, which is part of a group manifold. And the dynamical fields of the theory are the components of these group vielbeins of this manifold, okay? And what we want to interpret as symmetries of the theories are general coordinate transformations in this group manifold, okay? So this is the framework in which we work when we speak of the group manifold approach or supergroup manifold approach for supersymmetric theories to gravity and supergravity. Now, we know that supersymmetry must be related to some kind of fermionic coordinate transformation, since the commutator of two supersymmetry gives a coordinate transformation, bosonic, and then we introduce superfields. Introducing superfields, we introduce also, we can construct superspace actions, and the superspace actions must be invariant under superdiffeomorphism. And you interpret, once you integrate with Berezin integration and you obtain a space-time theory, a space-time Lagrangian on n-dimensional space-time, you interpret supersymmetry as a remnant of the invariance under super diffeomorphism in the fermionic directions. There are two systematic procedures then to construct supergravity theories. There is the superfield action that I just discussed and the supergroup geometric action that I discussed a few transparencies before. Now, of course, this in the group geometric approach requires integration on supermanifolds with forms. And the idea is, are there super top forms? Now, if you naively expand a form depending on x and theta in differentials dx d theta, you see that you have a problem because the d theta, since theta are fermionic coordinates, the d theta commute. They do not anti-commute, they commute. So there is no limit on how many d theta you can put. And the exterior derivative of a form with d dx and maximal number and all the d theta you can write cannot be a top form. So here you have a problem, but this problem is resolved by using integral forms. Integral forms you can do by expanding any form, confining the d thetas inside delta functions so that this form has compact support as a function of the even variables. And then you can show that these that I will call an integral top form is closed, and it can work as a top form for supermanifolds. And this is what can be used. Analogously, you can define integration on a submanifold of a supermanifold by the use of the Poincaré dual that corresponds to the choice of the surface you are integrating on a submanifold, and this allows you a consistent theory of integration, including integration on submanifolds. Integration on submanifolds brings you to some interesting result, and this will be the last transparency. The first interesting result is that these two formulations with the group geometric approach and superfield approach can be directly related by judicious choice of Poincaré dual. In fact, this reduces to this when I use this Poincaré dual. This Poincaré dual differs from the naive Poincaré dual that projects on space-time by a total derivative, and then you can prove that these two actions are equal when also the exterior derivative on the Lagrangian is 0. So this is the first immediate result you get out of this formalism. The same procedure will be applied also in the equal 4 and in the equal 4 n equal 1 n equal 2 super Young Mills. This is work in progress. Okay, with this I'm finished, and I thank you for your attention.
Okay, there is a question from Rita.
Yes, Rita.
Well, Leonardo, it's a very, very good talk. I enjoyed it immensely. So I have two questions which are related. So the first question is about the cohomology of integral forms. That is, do we get the usual, I mean, the non-super cohomology, or do we get surprises? That's the first question. And the second.
Sorry, you asked about cohomology?
Cohomology. Can you view cohomology? First, the second question, which I'm really interested in, is the Kähler structures. Do they get like some interpretation in this integral forms business? Because I have the feeling that, you know, the Kähler supermanifold is important for super space-time, and I wanted a comment from you. Thank you.
Now, cohomology has been or is being investigated by my collaborator Antonio Grassi, who is together with Cremonini and Catenacci, has been making a study of cohomology for this sort of integral forms. And the results are interesting. In fact, they extend what we know of cohomology for usual de Rham and Chevalet. And the results are interesting because they explain some sorts of phenomena that in the purely bosonic case were seen more or less as coincidence. And in fact, I'm not sure this has been published, but probably Antonio could comment on this. So I think there is a rich cohomological structure, but I'm not an expert on this, and I would prefer to leave this discussion to Antonio. For the second question, I really do not know. I agree with you that the Kähler structure should play an important role, but I haven't used it so far.
Thank you. If there is Gaetano Fiore.
Ciao Leonardo, very nice talk.
Ciao Gaetano.
Some questions. Question: what happens if you take the derivatives from the right instead of from the left when you derive the equation of motion? You get equivalent?
No, they are not equivalent. They differ by signs. And there is a formula that relates the two, but it is just a sign that depends on the grading of the form in the numerator and in the denominator.
The equations of motions are equivalent, no? Aren't they?
The equation of motion are equivalent to the usual equation of motion, yes.
I mean, in the two ways, they are equivalent to each other.
Well, yes, and to the normal ones.
Okay, thank you.
Yes. It doesn't matter. You can formulate the variational principle, putting the variation on the left or putting it on the right. It gives the same equations of motion.
Okay, I don't see other questions, so we can thank Leonardo again.
Thank you.
Now we come back live, I don't know what to say, in the flesh, with Thanasis Chatzistavrakidis. I think it's a one-loop approximation of the pronunciation. And the title of the talk is Twisted R-Poisson Sigma Model.
Okay, I believe you can hear me. So first of all, I would like to thank the organizers and especially Harold.
Do you have a microphone for the remote? Okay.
Can you hear me? Well,
I couldn't see the microphone, which covered by.
No, Jonah. Okay, as I was saying, I would like to thank the organizers for putting together this meeting, especially Harold and Kostas, and for inviting me. And I would also like to dedicate my talk to the memory of John Nadeau, a dear friend and somebody from who I learned a lot during my PhD years. What I'm going to talk about is a class of topological field theories that I described in this paper here quite recently. And let me start right away with my motivation for studying this class. So, well, the general motivation, I would say, is that topological field theories appear to be very interesting in very diverse physical problems and also in diverse dimensions. So, we know that in 2 dimensions we encounter the prototype TFTs, which are the A and B models described by Witten in the 80s, and they describe topological strings. In 3 dimensions, we encounter, of course, Chern-Simons theory, for which the list of applications is immense. We heard some talks related to that by Dimitra, Nair, and also by Volker earlier. In 4 dimensions, there is a lot of interest also in the spirit of describing topological states in quantum matter and response to perturbations using effective field theory. And these effective field theories are usually topological field theories. Highlights maybe include topological insulators and topological superconductors. So the message here is that topological field theories are interesting in physics, and they are interesting in many different dimensions. My second motivation comes from a line of research that starts with work of Ed Witten in the 80s, and then Albert Schwartz, and eventually Alexandrov, Konchevich, Schwartz, and Zaboronsky, till more recently the work of Dima Rothenberg, that regards the Batalin-Vilkovisky quantization of topological field theories. And in particular, what is its geometric formulation, something that led to the development of the so-called AKSZ construction for topological field theories, which is a geometric and unified way to find the BV quantization of TFTs. Here, in 2 dimensions, this construction gives you the Poisson sigma model. So the Poisson sigma model, after gates fixing, it gives you the topological A model. So this relates to the first bullet point here. In 3 dimensions, the AKZ construction gives you the so-called Courant sigma model. This is a 3D TFT with an underlying geometric structure of a Courant algebroid. And in special cases, this TFT results in Chern-Simons theory. So it is sort of Chern-Simons theory again. So again, it relates to the first bullet point. And the underlying geometric structure behind this construction is the so-called QP manifolds, and I will come back to this a little bit later in my talk. The third piece of motivation regards Vezumino terms. So in these TFTs, we can include Vezumino terms, which can be, for example, brane couplings or something like that. And Vezumino terms, in general, twist the geometric structures. And moreover, by twisting the geometric structures, it can present obstructions to having a QP structure and consequently to apply the AKZ construction. So a particular instance of this was described a couple of years ago by Noriaki Ikeda and Thomas Strobel, who studied the 3-form twisted Poisson sigma model and tried to find their BV action. And indeed, they found it, but not with the AKZ construction. They discuss very explicitly why this construction does not work in that case. But this you can also imagine, for example, for 4-form twisted Courant sigma models and things like that. I'm going to discuss more about this later. And from a different angle, if you wish, the 2-dimensional Poisson structures and Poisson sigma models and the 3D Courant sigma models relate essentially to all above points. And moreover, they are interesting in themselves. For example, as we all know in this community, Poisson sigma model is strongly related to formation quantization, the Konchevich star product. But also the Courant sigma model seems to be related to non-associative star products. This is work by Peter, who is sitting there in the back, Richard, who was a previous speaker. So this is also a piece of motivation. So in this talk, I would like to answer mainly the following question. So how 2-dimensional are Poisson sigma models? So in a way, I want to see if I can construct topological field theories with Vezumino terms, which are induced by a Poisson structure and potentially by some extras which are compatible with it in dimensions 2, but also higher, as high as you like. And then doing this, I would like to draw some general lessons regarding twists. What can we twist? What kind of geometric structures we can twist and how? And about target space covariance and target space geometry. And well, something that I'm not going to talk about today, but I will comment on it, about the BV formalism in this context. So just to give you the main pointers of what I'm going to talk about in the technical part of my talk. So I'm going to discuss a generic class of TFTs in p+1 dimensions, starting from 2 and going as high as you like, which have what I call a target space geometry based on a H-twisted R-Poisson structure. So this will consist of a bivector pi, which is Poisson, an antisymmetric p+1 vector R, and a p+2 form H, which will be the Versumino term, which is closed, and all these structures will have some compatibility condition between themselves. Now, moreover, I will focus a lot on discussing target space covariance, because a lot of work on this kind of structures has been done before, but in a way that things are defined on a local path. So I would like, so for me it was not obvious at all how you can go beyond local patches. So I will discuss a little bit target space covariance and suitable connections that are related to it. In particular, I will discuss the role of so-called E connections and their E torsion and E curvature in the particular case for a vector bundle E, which is the cotangent bundle. There was a recent follow-up paper by Noriaki Ikeda a couple of weeks ago where he discusses a general vector bundle. So this will give us a bit more global perspective on these things. Next, I would like to discuss a little bit the relation to Q manifolds. Basically, what I want to just highlight here is that in these cases that I will study, you will have a Q structure, a P structure, but you will not have a QP structure, which is the main reason that the AKZ construction cannot be applied per se. And finally, apart from this generic case that I described, I will discuss a little bit how you can deform these theories and find some islands of topological field theories in special dimensions, at least in the field content that I will assume here. And we will see that there are even more relaxed structures here appearing, like bi-twisted R-Poisson structure. I will describe what it is towards the end of my talk. And these kind of deformations in this class of models can happen only in 2, 3, and 4 dimensions. Okay, so well, this looks like a long list of contents, but I will try to be brief in each one. So I'm going to briefly introduce Poisson and twisted Poisson sigma models in 2 dimensions in the beginning. Then I will move on to this generic class of TFTs that I want to discuss in any dimension. I will highlight some things about the target space covariance and about the Q manifold picture. Then I will discuss briefly about these deformations and this bi-twisted R-Poisson structure. Hopefully, I will have time to make a few comments about the BV action in this case, and then I will conclude with some outlook. So to start with, let's take a look at the twisted Poisson sigma model, which was described by Klimchuk and Strobel 20 years ago. So this is a 2-dimensional topological field theory with 2 fields. So it has a set of scalar fields X and a set of space-time one forms A, which are defined like this. And the action of the model is this simple action here, which includes also a Versumino term, where H is a closed 3 form. Now, the target space of this theory is what is called the twisted Poisson manifold, first introduced by Pavel Shevera and Weinstein, also 20 years ago. So a twisted Poisson manifold contains a bivector pi and a 3 form H. The 3 form is closed, as you see. And the bivector is not Poisson, it's twisted Poisson, and the lack of Poissonness is controlled precisely by the 3 form H by contracting it with 3 bivectors pi through this formula. Now, this model has gauge invariances, so it is invariant under these gauge transformations. So there is a single scalar parameter, which is epsilon, and you see that the transformations on the scalars are essentially transformations along the Poisson structure, and the transformations on the one forms are essentially Young-Mills type nonlinear transformations, including also a little bit bizarre term that contains the Vesuvino free form here, and a little bit bizarre combination of one forms. I will come back to this. And the classical field equations for this model are these ones here. And one thing that I would like to highlight is that in both the gauge transformations and the field equations, there are non-tensorial quantities appearing, in particular the derivative of the Poisson structure. Well, not of the Poisson, of the twisted Poisson structure, of the bivector. Okay, let's look briefly at the target space covariance of this model. So, first of all, the action is quite easy because both these and these terms are quite ready. Actually, they are well-defined two forms, as discussed in this paper here. And also the gauge transformation for the X and the field strength for the X are also quite ready. They are just simply as that, like that. For the one form, things are a little bit more complicated because we have these non-tensorial structures appearing there. So for this, we need to introduce a connection on the tangent bundle. So this is a connection with torsion, actually, which in a local basis, it has components, these gamma symbols here, and the gamma symbols contain a symmetric part, which is like the torsionless affine connection on Tm. And the rest is essentially the torsion, which I denote with capital theta here, which is again controlled. It's the contraction of the bivector with the free form. This also induces, of course, as usual, a dual connection of the cotangent bundle with the opposite coefficients, right? This is discussed also in this paper of Noriaki and Thomas. Now, if you try to look what would be the covariant transformation of the one form and the manifestly covariant field strength, you will find eventually that they look like this. So this capital D here is the covariant exterior differential that is induced by the connection, and this T here is what is called the E torsion. It's actually not related to this theta directly. So this T is actually the affine connection without torsion acting on the bivector, and it is called the E torsion or T star M torsion here because there is a notion of higher covariant derivative whose entry, basically the lower entry is not a vector field as usual, but it's in one form. And then there is a usual formula for the torsion, but for this higher covariant derivative. And you can note that this torsion here does not see even the free form H, right? All the dependence here on the free form is in the exterior covariant derivative capital D. So this bizarre looking term here is actually absorbed together with a D epsilon here. Okay. Now, so this is a lesson we can draw from the Poisson sigma model, which is much simpler. And now I'm going to introduce this new class. So this class of TFTs is defined on a p+1 dimensional space-time. It has a set of scalar fields, which are like sigma model maps of this type. And it has a Vesuvino term again, but this time the Vesuvino term is a p+2 form, because we are working on p+1 dimensions. And I assume also that it is closed. So dH is 0. A Poisson bivector here. I will assume that the field content of my theory contains, apart from the scalar fields X, a set of one forms A, which take values on the cotangent bundle on M, on the pullback of it, of course, by X. A set of P-1 forms, Y, which take values in the tangent bundle, and a set of P forms Z, which take values in the cotangent bundle again. And now, with this field content, I can write down a generic action functional in any dimension from 2 higher by writing down all possible terms that can be written in any dimension. And this looks like this. Now, highlights here is that there is a pi. So this pi is a Poisson here. It's not a twisted Poisson. It's a Poisson structure. So the Poisson vector is contracted with this P form and this 1 form. We are in P plus 1 dimensions. But also there is a term that involves the derivative of Poisson, right? So you could complain already that this action is defined only on the local parts, but actually this is not quite true. It's just an artifact of the presentation. And then there is this P plus 1 form R also that can be written here. And there is the Vesumino term, which is a P plus 2 form. Okay, so now the target space of this theory has what I call the twisted R-Poisson structure. So it's a manifold with a bivector which is Poisson, a P plus 1 antisymmetric vector, and the P plus 2 form, which is closed, that they satisfy this condition here. So the Schouten bracket of the 2 vector with a P plus 1 vector, which is a P plus 2 vector in total, is controlled by the P plus 2 form, like this, by contracted it with P plus 2 appearances of the bivector pi. So this is essentially sort of reminiscent of the twisted Poisson condition, but it's not quite that, because you can notice the following. So here, twisted refers actually to H. It doesn't refer to the Poisson vector, right? So for H equals 0, we still have an R-Poisson structure, which is untwisted. And then for H equals 0 and R equals 0, you get a genuine Poisson structure, but now the sigma model is in higher dimensions. Now, this class of models also have a set of gauge symmetries. I mean, these long expressions. Actually, for X and A, the gauge symmetries are the same as the Poisson sigma model. It's just that one has to find the symmetries for the rest of the fields. This is the complicated version, I would say. You see that again there are non-tensorial expressions like d pi's and dd pi's, and there is the generalization of this term here in P plus 1 dimensions, which is a complicated sum of products of stuff. The point though is that this action that I wrote in the previous slide is gauge invariant if and only if this is indeed a twisted R-Poisson manifold of order P plus 1. And similarly, one can write down the 4 field equations of the model, which I will denote as F, G, Cal F, and Cal G, which start with the corresponding D of the fields. Okay? Now, revisiting a little bit target space covariance, well, actually, maybe I will not go through this slide in great detail, but we have to introduce a connection again without torsion on Tm, on the tangent bundle, and its dual connection on the cotangent bundle. Now, then we can basically start studying how we should define the covariant expression for A. The story is the same as the twisted Poisson sigma model. Let me not explain exactly the details here, but the point is again that you find these expressions for the covariant transformation of A and the covariant field equation that involve the torsion of the E connection on T star M. Now, of course, this you have to do it for all the fields, right? So for the other fields, it's actually a little bit more complicated. It requires a little bit more work. And actually, the formalism directs you already that you have to make some field redefinitions. So I define here, let's say, covariant field Z. So I remind you that this is the P form of the theory, and this is the P minus 1 gauge parameter of the theory. So yeah, maybe I forgot to highlight this. So there are 3 gauge parameters, of course, here, epsilon, chi, and psi of degrees 0, P minus 2, and P minus 1. Okay, but the point is that the final results have a very nice covariant form here. And what I wanted to mainly highlight is that the appearance of some interesting quantities. So one is, again, the T star M torsion, the high torsion that we encounter here and here. But then there is also the so-called basic curvature S, which is defined in this invariant way. Here, R circle is the curvature of the torsionless connection on Tm. 5? Okay. And then there is this tensor, which is like P plus 1 contractions of pi with the P plus 2 form H. Now, using this, you can rearrange the terms in the action and write it in a very nice covariant form like this. So you see that now these things are getting into perspective, because similar actions have been written also by us, by Lara, Olaf, and myself, and other people like Peter. And the point is that these actions were only defined on local parts. This is the expression which is the covariant expression of these actions. Okay. Now let me go through briefly on the Q manifold picture. So I remind you that the Q manifold, or differential graded manifold, is a graded supermanifold which is equipped with a degree 1 homological vector field. So a vector field that squares to 0. And there is this beautiful picture that was found by Weintraub in the 90s, that every Lie algebroid, namely every vector bundle that has a Lie algebra structure and sections, has an equivalent formulation in terms of a Q manifold by just taking a degree shifted vector bundle and equipping it with a homological vector field. Now, for the twisted Poisson structure, for example, there is a Lie algebroid on the cotangent bundle. This Lie algebroid, you can equip it, you can take the degree shifted cotangent bundle. This means that you take the base coordinates, the bosonic base coordinates x, and then you assign a degree 1 coordinate to the fiber coordinates, which I call here xi. And then you can write a vector field like this. And if you square to 0, you see that the result is exactly the twisted Poisson condition. Now, similar story holds here. So for the twisted R-Poisson structure, the relevant manifold is this second order cotangent bundle, T star P, T star 1M. So this has degrees 0 on the base, it has degree 1 on the first fiber, and then it has the dual degrees, which are P minus 1 and P. So all these are coordinates of this degree. And this is a vector field with respect to the derivatives of these coordinates, that when you square it to 0, you get that pi is Poisson, and the twisted R-Poisson structure condition holds. And now what I wanted to highlight here is that since the target is a cotangent bundle, it's naturally equipped with a symplectic structure, a graded symplectic structure, and that will show it has a Q structure too. But if you do the calculation, you will see that the corresponding symplectic form is not invariant under this vector field. And the non-invariance is exactly due to the P plus 2 form H. So only when this is 0, this is a QP structure. So the lesson to draw from this is that the Zumino twists obstruct the QP-ness, and then standard AKZ is not enough, which is in accord with the results of Ikeda problem. Now, briefly, let me go a little bit further and ask what other terms with this field content that I had I can add to my action. So these terms are possible only in specific dimensions. So in 2 dimensions, 3 dimensions, and 4 dimensions. And this is a list of them. So for example, a Z term, it's a 2P form. So you can only write it in 2 dimensions, right? For P equals 1. And similarly other terms. And let me just guide you through a little bit what you get through this without going into technical details. So in two dimensions, you choosing different deformation for the action, you get, for example, H twisted R-Poisson sigma models of order 2, which is like part of the generic class, but you also get the ordinary H twisted Poisson sigma models with BF theory. In 3 dimensions, R is a 3 vector, and the theory essentially is more or less a Courant sigma model twisted by a 4 form. And in this case, you get something that I call bi-twisted R-Poisson, in the sense that now also pi is not a Poisson vector, but its non-Poissonness is controlled by this combination here, where S is the additional ingredient. It's a 3 form, but it's not closed, and it's actually the exact part of the Vezumino term H. Okay, let me, at the interest of time, continue. There is also a 4D model which is quite interesting, but I'm not going to discuss it now. Let me say a few words about the BV. So in the 2D twisted Poisson sigma model, the action was found only recently. I mean, the model was known for 20 years, but Ikeda and Strobel found it just a couple of years ago. And the main features is that you have a single scalar parameter, so you have one ghost, but the system is open, so you have to do BV, because the BRST operator that you would define does not square to 0. And actually, it squares for the one forms to the basic curvature, and that's a very interesting aspect here, because here this appears only at the BV level, at the BRST level. In the higher models, it appears also already at the classical level. So then you can try to find the solution to the classical matter equation, and this involves exactly this basic curvature. Now, this includes a term quadratic in the 3 form in the Poisson model, which is exactly why one couldn't see these in the AKSE construction. Now, for my case, it's something that we are working on with my student Grgur Shimulits and Noriaki Ikeda. The situation is more complicated because you have a high state reducible gauge theory, so you have many ghosts and ghosts for ghosts. So, and all these create BRST operators that do not square to 0. But okay, we are very close to determining the BV extension, and we are going to report on this soon. So please give me half a minute to conclude. So the take-home messages from this talk, I would say, is that first of all, Poisson and twisted Poisson sigma models is not a strictly two-dimensional story. So there are a lot of interesting models in higher dimensions too. Covariance is a very delicate issue and requires higher structures like connections on higher vector bundles, curvatures and torsions constructed from these connections. And that Versumino twists complicate matters, they obstruct QP, but nevertheless, you can work with it if you appropriately follow the lessons of the BV formalism. Now, just to do some contextual advertising, there is another interesting thing, which is how to find the BV action for direct sigma models, because in this case, you have a Q structure, but you don't even have a P structure. You don't have a symplectic structure. Nevertheless, this is doable. We are going to report on this soon with Thomas Strobel, Lara, who is here, my student, my postdoc. And well, also with my student, we had some interesting work on which is based on transitive courant algebroids, which results into twisted Jacobi sigma models. We can discuss this over the coffee break if you want. And yeah, maybe regarding some open directions, one thing is what I already told you. We are planning to construct the BV action, at least the classical one, and then proceed to the quantization. I'm very interested to understand whether this can be extended to so-called homotopy Poisson structures or P-infinity structures, which were described by Voronov and Catano and Felder several years ago. And of course, with a little physics guidance, we should also try to see for other Q manifolds what kind of useful topological field theories we can write that can lead to some interesting physics. So I will stop here. Thank you.
Thank you. We are a little short of time, but if there are questions. Stratos is much better than I to spot questions.
For a nice talk. The question, the corresponding star product, what kind of properties will it have? Can you guess it? I mean, you're going to construct it, but you can already guess it, right?
Well, I mean, as you know from your work, I mean, in the Courant case, the star product turned out to be a non-associative one, right? As you already said, I haven't studied it yet. This was the first step. This is something that we plan to do. But
I was wondering how the R will come in. The R. I was wondering how the R tensor will come in. The H is clear.
Yeah, I don't exactly know, because like in your case, the R tensor was a 3-vector, right? So it came in naturally. So if you ask for higher dimensions, I don't exactly know how R would enter the star product. I mean, I haven't studied it yet. And it's not also an easy matter. I mean, it requires a lot of work, I would say.
Okay. Unless there are other urgent questions, let me see the chat. But I think that if somebody, okay, I don't see. There is nothing, no? Ah, no, there is Ikeda, sorry. Okay, please, Noriaki, you can.
I'm Noriaki. Can I ask about the bi-twisted case? Can we construct topological sigma model for the bi-twisted Poisson sigma model? Bi-twisted Poisson structure?
In how many dimensions? In 4, yes?
Yeah, in general dimensions, in bi-twisted case.
Right, okay, yeah, so yeah, the question is if we can construct these bi-twisted cases in arbitrary dimensions. I think, well, okay, first of all, for the field content that I have, for the braided supermanifold that I have, the answer is no. This is a feature of 3 dimensions with this field content, because otherwise these extra terms cannot be added. However, like if one is takes the attitude that we can change the field content, for example, in this P infinity context, that you can introduce also intermediate P form fields between the 0, 1, P minus 1, and P, it's very likely that you can indeed find some higher structures like that. So I think that even this bi-twisted R-Poisson is a part of this homotopy Poisson, these P infinity structures. So I would say that it is potentially true that you can find these in higher dimensions too, but not with the field content that I had in this talk and in this paper.
Oh, thank you.
Thank you, Noriaki.
Okay, I think we can wrap up this session. We thank again Thanasis. And we'll reconvene at 4, no? We reconvene at 4 with the talk of Alessia Platania. I thank the people who are present.